Okay, so welcome to the course today. We are going to continue our investigations of the fundamental matrix and the essential matrix. And so far what we did, we described what is the fundamental matrix and essential matrix, how can we derive that, and how can we express it as a product of rotation matrices, calibration matrices in terms of the fundamental matrix, and a screw symmetric matrix encoding the baseline. Today we would like to take the other way around and say how can we actually obtain the fundamental matrix and essential matrix if we do not know where our camera is, but we know something about corresponding points in images. So consider we have two images, like those two images of the same building taken under different conditions, potentially, as long as the geometry of the object doesn't change, that's not critical, and we want to know the relative orientation between those two images. So how can we actually do that, or how do we want to do that today? We want to look into estimating the baseline as well as the rotation parameters based on the knowledge of corresponding points. So if we know some corresponding points, like those points, which let's say I manually label them. So I manually say, okay, this point over here corresponds to this point over here. And then I say, okay, this point over here corresponds to this point over here. So I'm doing these correspondences manually. Maybe I have a smart algorithm which does this. This is great, I can do that, but we can also assume that they are given by a human. So we assume we have those correspondences. So we know that this pixel over here corresponds to this pixel over here in the other image. And what we now want to know is we want to compute the fundamental matrix and essential matrix with the goal of obtaining, for example, the rotation and the baseline information about the camera from which location these images have been taken. So that's kind of the focus of today, and we look into different techniques to do that. We will study today the so-called direct methods. That means I can directly compute a solution without an initial guess. This may not be the optimal solution to achieve that, but this can serve, for example, as an initial guess for a least squares solution. And this is a technique which provides you already a pretty good estimate of these for the essential matrix or the fundamental matrix. So we will start with the fundamental matrix, look into kind of the standard algorithm, which is so-called 8-point algorithm. Then we look into how can we do that? Can we do better? And just we'll very briefly sketch an idea how we can do that with a smaller number of corresponding points. Then we are going to look into the essential matrix, and then the question, how can I actually obtain the rotation matrix and the basis if I have an essential matrix. So that's kind of the rough schedule of today and kind of the three big blocks, whereas we will discuss different techniques in those blocks and how to do that. And there's also the further information, it's more in detail, so we will start with the so-called 8-point algorithm for the fundamental matrix, then see if we can do that even with a smaller number of points, so with 7 points. We look into the computation of the essential matrix using basically the same algorithm, slightly adapted, and then look into special cases. So if we have some background information about how the points have been selected, or if I know already, let's say, the rotation between the two cameras, but on the baseline, how I can do that more efficiently. And then we'll come to the 5-point algorithm. We won't discuss the 5-point algorithm in detail. This is today the standard approach for estimating the essential matrix given corresponding points. It only needs 5 corresponding points, but we will very, very briefly sketch the idea, and then finally look into the last block, how do we obtain the rotation parameters and the baseline, given we have an essential matrix. So that by the end of today, if you have images and corresponding points, you should be able to compute the relative orientation. Just knowing corresponding points, not knowing anything further about the camera. If you use the essential matrix, then your camera needs to be calibrated. For the fundamental matrix, it doesn't need to be calibrated. Okay? So that's kind of the topic of today, and we start with the first block, computing the fundamental matrix from corresponding points. First, quick reminder, how does the fundamental matrix look like? So we have this expression over here, so involving calibration parameters, rotation parameters, and the baseline. And the important thing is also the block we're going to exploit again is this coplanar constraint. That means if I have corresponding points, then multiplying it from the left and the right hand side to this fundamental matrix must be 0 if this is if these 2 points are corresponding points. Okay, and that's what we're going to exploit. So far, we looked into two means for obtaining the fundamental matrix. We assume we know the calibration matrix, the rotation parameters, and the baseline, then we can directly compute it, or we just know the projection matrices of the two cameras, and we also can directly compute that. That's what we have done so far. But the question is, how can we actually compute f if we only know corresponding points in the images and nothing else? So that's kind of the problem that we're addressing now. We can start with the problem formulation. Consider we have those corresponding points, so in the first image and in the second image, and we have n of those images. We want to compute this fundamental matrix over here. So this is kind of our target. I told you already that we are going to exploit the coplanarity constraint. Of course, this is kind of the key information that relates corresponding points and the fundamental matrix. Do you have any idea how we could start trying to estimate the fundamental matrix given that we had those corresponding points? And we don't know anything else about our camera. So we have two images, labeled those corresponding points. Any idea what we could do to get a glimpse of from which location those images have been taken up to the scale?
Yeah. We can use it, what's it called?
Coplanarity constraint?
Coplanarity constraint.
Yes, this is what we're going to want to exploit, that's true. And that's how it looks like. Anything else? What can we do? So these x are kind of given. These are our corresponding points where we know the pixel locations. And f are our unknowns. So the elements of this matrix are our unknowns that we want to estimate. First thing we can do, we can actually expand this expression just according to the definition. Say, okay, these are our known points, and these are our unknowns. So we know that we have 9 unknowns. So these guys are our unknowns. And what we now want to do is we want to build up a system of linear equations that has those 9 parameters as the unknowns. The goal is then to solve this system of linear equations and with the solution of this system obtain those 9 parameters. And we can put our 9 parameters in and we have our fundamental matrix. It's kind of the overall scope. Okay, so the first thing that I want to express here is that the functions that we have, given that these are known parameters, and I have a function which depends on those 9 parameters, on these individual fij's, that there's a linear dependency. So we have just a linear function of those elements. And this becomes clear if I actually compute this product of matrix and 2 vectors. So what is this expression over here? I compute this by multiplying x prime with f11 x double prime. So this gives me a first block over here. Just in this case, just rearranged. I can do the second thing as well. I can say, okay, then plus this element multiplied with this element multiplied with this element. This element over here. And I can simply continue that and so on and so forth. So I can actually do that and get this equation which consists of multiple sums. And the key important thing is that in every of those elements over here, fij is a linear element. It linearly depends on these 2 known parameters that I have. So these are knowns, x are knowns, and f are the unknowns in this case. So I can actually slightly rewrite that and kind of can group all those guys together for all elements, put them into one vector over here, and can do the same thing for my vector of unknowns over here. Well, the only thing I've done now, I've rewritten this product of 2 vectors in a matrix, which is 3 by 3, into a product of 2 vectors in the size 9 by 1. Because we obtain 9 elements through these multiplications. And I can simply rewrite this in this form. And this kind of, again, emphasizes the fact that this is a function which is linear in f. So it's a linear function, linear dependency. So I can again then take this expression, say, okay, I'm going to rewrite this as a product of a vector A and a vector F. And this is exactly my vector A and my vector F. So if I compute the product of these two vectors, I have my equation which should be 0. This is clear up to this point what I've done. I've just rewritten the term, and the goal was, why have I rewritten this? In the original formulation, those 9 unknowns were sitting in my matrix over here, but I want to have a vector of unknowns. So just kind of rewrite this in this vector form. Okay. And so what I've done now is exactly the same thing we have done in the second lecture of the course with the Kronecker product. So what I've exactly written here is the Kronecker product of these two individual elements, these two vectors. So these are all combinations of the individual dimensions of these two vectors. And then vec of f, which is just a form which takes a matrix and puts it into vector form, just stacking the elements on top of each other. So if I have a matrix, let's call it A, and it's a 2 by 2 matrix which has the elements A, B, C, D, then what vec A does, simply turn that into a vector which says A, C, B, D. So just takes those elements and stacks the columns on top of each other. This kind of, I can actually do this rewriting in general for a general product of two vectors in a matrix, especially in this here. And we actually use this from time to time whenever we want to turn the elements of a matrix into a vector of unknowns. Okay, so we have that. Okay, we have that, and we did that now for. So we get this expression over here for each corresponding point. So every corresponding point generates me one of those coplanarity constraints. So it's still exactly the same coplanarity constraint that I had before, just slightly rewritten by rearranging those elements. None of the elements has been eliminated or anything like this. I've just rewritten those elements of the coplanarity constraint into this form that I have a vector multiplied with another vector, and this should be 0. This was done for one point, for one n. I have, however, capital N of those corresponding points. So I can actually repeat this process and do this process for every pair of corresponding points. So for the first pair, for the second pair, third pair, and so on and so forth. And if I get this, I can simply say, okay, from this expression for one corresponding point, I simply build a matrix A, which takes these individual vectors an here as their individual rows. The first row corresponds to the first pair of corresponding points. The second row corresponds to the second pair of corresponding points. And I now build up a matrix. And if I multiply this matrix with my vector f, this should be 0. So it's just a concatenation of the coplanarity constraint for all points. So just to summarize this, because it's actually not very difficult. The only thing we have done, we have taken our matrix, the matrix contained of unknowns. We turned that matrix into a vector just by stacking them on top of each other. And then I defined this new vector A, so that if I multiply A with this vector f, I obtain exactly the same elements I would obtain if I would multiply the vector matrix vector in terms of the coplanarity constraint. I do that for one corresponding point, or one pair of corresponding points in the left and right image. And then I repeat this as for the first step. And then I repeat this process for all the corresponding points that I have. And so I get a number, so if I have n corresponding points, I get n of those products. And I can simply rewrite this again by taking those vectors and put them into matrix form, and then multiply A with f equals 0. And this is my coplanarity constraint for all the corresponding points. So what I've done now, I've turned the coplanarity constraints of the individual pairs of corresponding points into one single equation where the unknowns are one vector, 9-dimensional, that contains the individual elements of the fundamental matrix. So the only thing I have to do now, if I want to compute my unknowns for my given matrix A, I need to solve this system of linear equations. And this is a 9-dimensional vector because I have 9 elements of my fundamental matrix. So how do I solve such a system of linear equations? How can I do that? This type of equation, ax equals b, or in this case af equals, no, ax equals 0, in this case af equals 0 because f are unknowns and not x, as is typically the case. Something which is called SVD, singular value decomposition, which you all should know, which I can actually use to compute, to solve this system of linear equations, which provides a solution to this system. And this solution f are those elements of the fundamental matrix. So if I solve this, if I obtain my vector f, then I can simply need to rearrange those elements again and have my fundamental matrix. So if you look to this equation, what it says is that basically f is a right singular vector of this matrix A, and this is the one which corresponds to the singular value that is 0. So this matrix A has one singular value which is 0, and f is the corresponding singular vector, so the right singular vector corresponding to this one. Okay, so the question is, how many points do I actually need in order to build up this system? We said f is a 9-dimensional vector. So how many corresponding points do I need? 9 would be the straightforward solution to that. I know, however, something about my fundamental matrix. And the easiest thing I know is that it's a homogeneous matrix. And the homogeneous matrix has only 8 degrees of freedom. So what I need is 8 corresponding points, because matrix A has the rank of at most 8. We have this rank deficiency we also discussed. We can actually do better because we know that f has 7 degrees of freedom. So in theory, 7 should be sufficient. But for this approach over here, we stick with 8 corresponding points. And we'll discuss then how we can use the 7 corresponding points afterwards. Okay, but if I have 8 corresponding points, that's fine, but I may have more corresponding points. And the more corresponding points I have, the better actually my estimate of the fundamental matrix should be, because there's always noise involved. The points are never perfectly determined, the locations of these corresponding points. So in reality, we have noisy measurements. We cannot locate with infinite precision the individual corresponding points in our images. So one of the things I can do is I simply take more than 8 points for computing my matrix A. The problem that I have, given that I have this small noise in there, that then my matrix A would not become a singular matrix. So would have full rank, or rank 9. Well, that's something I don't want, because I have this rank deficiency in my fundamental matrix. This was something which is core to the fundamental matrix. So what we see quite soon is that we actually need to fix this, or not fix this. What we're going to do in the first step is we say, okay, then let's take the right singular vector that corresponds to the smallest singular value. Because it's not 0 anymore if I have noisy measurements. Okay? Okay, so let's have a look how this works exactly. So I have matrix A, I compute my function SVD in MATLAB, or however I do that, and I obtain these 3 matrices. Okay, I can actually illustrate those matrices. So this is here I have n elements, 9 elements, and n is the number of corresponding points I have, so at least 8, but potentially more. Then I have this matrix U, which is an n by n matrix. I have this matrix D, which looks like this, and here I have the singular values on this element of the diagonal. and I have this 9 by 9 matrix here, V. So what are sitting in here are the individual singular values, and typically, depending on the function that you use, typically they are sorted, so largest one towards the smallest one down here. And if the last one is kind of the smallest one, in the perfect case 0, this element here of V transposed is the right singular vector that corresponds to this smallest last singular value of this matrix A. So if I have my matrix V, this V transpose V, this last column over here is my estimate of my vector F, which are the elements of the fundamental matrix. Okay. So let's start turning this into an algorithm. I want to write a MATLAB code which is able to do that. So the first thing we need to do if we want to write our MATLAB code is, okay, we have our function compute fundamental matrix from point pairs. And I have here x prime, x double prime. And the first thing that I do, I need to build up this matrix H. Matrix A, sorry, not H, A. And I can actually do that by saying every row in this matrix A is generated by the Kronecker product, where MATLAB gives you the function cron, of the individual vectors from our corresponding points. So just need to iterate over all corresponding points and then can compute this matrix A, which consists of the individual elements of x and x prime, kind of all combinations of them. Every row of A consists of this. Okay, then the next thing I need to do, I compute the SVD, so singular value decomposition of A, obtain my U, D, and my matrix V. And what I then do is I take the last column of this matrix V and kind of reshape it in a form that I turn this 9-dimensional vector into a 3 by 3 matrix. So this was kind of, so this element here is the singular vector, or right singular vector, corresponding to the smallest singular value. Okay, now I have my fundamental matrix F, and I'm happy. I think I'm happy. But in reality, I'm not happy. The problem why I'm most likely to be not satisfied with this, and this matrix F doesn't necessarily has rank 2. And the rank 2 was one of the constraints of this fundamental matrix. So I said before, I think I said rank 8 a few slides back, which was obviously a mistake. I was talking about the degrees of freedom, where 8, but so we have a rank 2 matrix. Sorry for this. So the fundamental matrix has rank 2. This is one of the constraints that I have. This F is not guaranteed to have this property. So I want to fix F. I want to fix this estimate of F so that I get a new matrix which is as close as possible to this matrix F but has this rank 2 constraint. So our goal is enforce rank 2 but come up within my new F should be as close as possible to the F or the F hat that we computed so far, but should have this rank 2 constraint. Any idea how we can actually enforce this? How can we generate a new matrix which exactly fulfills this condition? As similar as possible, but rank 2. So to help you a little bit, this estimate of F that we have is likely to have singular values, and if it does not have rank 2, one of those singular values, all the singular values are unequal to 0. But we said we're just very close to our solution. So it's very likely that one of the singular values is very close to 0, but it's not 0, but close to 0. And the two others are likely to be larger. So what I can do is I can replace a matrix F hat by a new matrix F by setting this one singular value which is close to 0 to 0. right? So the idea is I have a matrix F which doesn't have rank 2. I want to turn it into a matrix which is as similar as possible as F, but has rank 2. What I can do is I can inspect the singular values, take the smallest one, and set the smallest one to 0. In order to do that, I can again exploit the singular value decomposition, because what the singular value decomposition does, it turns A into this product of 3 matrices, and the matrix in the middle, the matrix D, is exactly the matrix which has the singular values on its diagonal. I simply take the smallest one out and set the smallest one to 0. That's kind of the trick that I'm doing. Yes, please. Okay, so how close does this value has to be close to 0? So the question is, it should be close to 0 if you pick your corresponding points correct. So you will have an error in your corresponding points because you can't locate them perfectly. And this is the only source of error that we have in here. So if you have very wrong outliers in there, this value may be very large compared to those others. And so this could be an indicator that you selected your corresponding points in a suboptimal fashion. But typically you should have one value which is very close to 0. I mean, it also depends on how many points you have. The more points you have, the larger the errors that you have in this process, because you basically accumulate the error of all the individual corresponding points. So what we do is simply we take our matrix F hat, and of F hat we compute an SVD. So we compute the SVD of F hat with U, D, and V transposed, and then say, okay, let's simply take those elements and modify D by setting the smallest singular value to 0. So take the 2 largest ones and say, okay, I replace this by this U, V transposed, and D I replace by just taking the 2 largest singular values. And then obtain the matrix F, which is as close as possible to my matrix F hat that I estimated from solving my system of linear equations, but which has this rank 2 constraint. So I can go back to my 8-point algorithm until here. That's what we had before. I only replaced F by FA, A for approximation. And then add another singular value decomposition, now not using the matrix A, but FA. So I'm decomposing my matrix F, which is a 3 by 3 matrix, using this SVD. And then I'm generating my new matrix F, which uses exactly the matrix U from the singular value decomposition of the approximation of the fundamental matrix. Take the 2 singular values, set the third one to 0, and then multiply with V transposed. And so with this approach, what I obtained is enforcing this constraint that the fundamental matrix has rank 2. And this is the full 8-point algorithm, or let's say the very basic form of the 8-point algorithm, which I can use in order to compute the fundamental matrix given 2 images and at least 8 corresponding points in those images. The more the better. Okay? So any questions up to this point over here? Okay. So there are a few things I need to be careful with in this setting. The first one is, if I solve this system of linear equation, I need to check, or it's a good idea to check, if there's a well-conditioned problem. So you can use the condition number, which tells you if you vary your input parameters a little bit, how much do the output parameters vary. And the smaller this condition number, the better the system that you want to solve is. We are working with these homogeneous coordinates, so if you have an image, let's say 3,000 by 4,000 pixels, and let's say I center the 0 around here, taking this pixel here into account would give me this vector over here. You can see already from this vector that you have some values which are rather large and some values that are rather small, which typically leads to a high condition number and a badly conditioned or ill-conditioned problem that you have. So what we can do is we can actually generate a new coordinate system which takes those points over here and maps it into a different coordinate frame where all the values are roughly along the same scale. And this leads to a better conditioned system, and this is numerically more stable. And this is actually essential for getting a robust version of this algorithm to do that. This transformation over here into a new coordinate system is actually a very, very easy one. The only thing that I do is, so the center of the image is the center of my coordinate frame, and then I scale this so that the points lie between -1 and 1. So they're all centered around 0 and take values between -1 and 1. So it's a very simple, it's called a normalization of the point coordinates. It's a transform so that either the center of the image or the center of mass of all the corresponding points, because I'm not interested really in the image, but in the coordinates of the corresponding points. So that the center of mass of the corresponding points is at 0, 0, and that the elements lie between -1 and 1, the individual coordinates. And then I can apply exactly the same approach that I did before to compute my fundamental matrix or essential matrix. So what I need to do for this conditioning, so this E should be actually an F. It's a copy-paste mistake, but it holds for E as well, so we can leave that here. So in terms of normalization, so what I do, I transform my system, my coordinate system, so that it is 0-centered and the elements lie between -1 and 1. Then I compute my fundamental matrix or my essential matrix. But what I then need to do, I need to actually turn it back into the original system. And so what I need to do that, if I have my essential matrix from the original points, say, okay, I transformed my points with my transformation T, turn that into X hat, and then I get this E hat or F hat over here. This is just the product of the essential matrix with the transform. So if I want to convert from the essential matrix that I estimated to the original essential matrix, I just have here T transposed T. So there's a very easy mapping between this transformation and the essential matrix that I computed, because I computed the essential matrix for this different coordinate system, and so I need to do the mapping back. Yeah.
So you talk about the essential matrix?
So yeah, so this is a mistake because I copied this. So later on we do the same with the essential matrix. I just copied that slide. So CE as F. I'm sorry.
I understood that, but I was not looking for the word. So the text should be determined fundamental matrix.
Yes. So because it's just so this matrix, this slide will appear later on when we talk about the essential matrix. I copied over and I seem to have forgotten to replace the E by an F and the essential matrix by a fundamental matrix. But the rest stays the same in here. Das gleiche, so this holds for the essential matrix as well as for the fundamental matrix, holds for both. Yeah. So sorry, I'm going to fix this slide. So this is one of the things, one of the normalizations that I need to do. There are, however, some situations where I can't obtain a solution.